Hello again, folks. Today we're going to be covering section 7.2, right triangle trigonometry. Here's a quick view of the calendar, just to confirm. This video will be for Wednesday, June 15th, so yes indeed, 7.2 is the section. The packet that I have for you consists of these pages. This is firstly an overview diagram I made of different perspectives, if you will, on right triangle trigonometry. That is the perspective that is the Pythagorean Theorem usage as a ratio in relation to an angle, and to determine basically coordinates, ordered pairs x and y. All right. Where we are today is basically here. This is a somewhat of an older view. It's still viewsful and will eventually return, but this is section 7.2 where we're at, the new stuff. Here again is my overview of functions for the semester. All right, we're in this category now. We're not going to be dealing with functions per se today, but we will go through sine, cosine, tangent, cotangent, secant, and cosecant. So just to more or less introduce those. This is something of an explanation, my attempt at explaining where these words came from. And this is a worksheet. If we were in person, I would prefer naturally to do this with the class. All right, I strongly believe that if you physically write something, you're more inclined to grasp the subject. It will be a little bit easier if you have built that reference in your own head. Anyhow, I'm going to have a printout of this completed available in Canvas, so if you're not watching, in theory, you could just print it. But humor me, all right, and I'll try to explain the details of this as we go through it. I hope it to be beneficial. Then there are special right triangles. This is going to become increasingly more important in 7.3 and beyond. The 30, 60, 90 degree and the 45, 45, 90 degree triangles. All right, they have sides that are always in this proportion, or these proportions, and these have side lengths in these proportions. Okay. This is something I drew from different class, but I want to refer to this alternate interior angles. Your textbook brings up something called angle of elevation and angle of depression. That's a fancier way of saying alternate interior angles. So I'm just going to point to that, and I think that's it. All right, so if you're following along, print that, and we'll just sort of add to it as necessary. All right, let me begin with this. Turn on the projector as always. Find my glasses. And adjust the lights. Okay, yes, definitely need to adjust this. Here's my overview diagram I mentioned. Think of, when we're going to be talking about right triangle trigonometry and actually triangles, think about the subject of today, this, which would be really section 7.2 here, all right, as being one of three perspectives of the same thing. All right, the Pythagorean theorem, good old Pythagorean theorem, is to say that the sum of the legs squared would equal the hypotenuse squared is still true. All right, it will never not be true. All right, but it's not imperative to think about things that way just right now. When we get into section 7.3 on Thursday and beyond that, chapter 8 perhaps, all right, this is going to be resurrected, albeit in a perhaps slightly different form. It'll change the lettering, right, to X and Y and R. Anyhow, the subject of today is the trigonometric perspective of right triangles, right? It's really quite imperative, right? Hypotenuse is always going to be, just as in the case of Pythagorean Theorem, the dimension that is across from the 90-degree angle in the quintessential right triangle, all right? However, all right, the ratios that you're going to see, which are sine, cosine, tangent, things like that, all right, are not in relation to 90 per se, they're in relation to another angle, right? And the side dimensions would be labeled, instead of, say, A and B or X and Y or something like that, they'll be referred to as adjacent and opposite in respect of that, right? Why adjacent and opposite? Because if you're explaining things in reference to the angle here, that is opposite of it, right? And the dimension that is down here is adjacent to it, right? So know those names, all right? Know those labels for what normally would be A, B, and C, say. All right, adjacent, opposite, and hypotenuse, just as it always is. Okay. Now, just a quick flash of that diagram that I gave you a while ago. This is the territory that we're entering now. And in the near future. All right. We had last talked about exponential and logarithmic functions, right? We're not really talking about functions per se today. However, these phrases, which you may have seen if you've ever tinkered with your calculator or even just a scientific calculator, sine, cosine, tangent, cotangent, secant, and cosecant, they are really the subject of today because these unto themselves are ratios, right? The way that they're presented here are as part of a function. They're the function y equals such and such, right? But by alone, right, each is a ratio of side dimensions, of sides of a right triangle. Cosine, sine, tangent, cotangent, secant, and cosecant. And it would be strategic to sort of memorize them in that particular order. All right. Now, if you're wondering where these names came from, they're more or less borrowed from geometry. In geometry, there is famously a tangent line, a secant line, and a chord. All right. Let's start with secant and tangent. All right. A tangent is something that touches a curve, or in this case, a circle, at one point. So you see, this is a tangent line here as an example. It's just touching the circle on the edge right there. All right. A secant is something that you say cuts or intersects at 2 points. So this is penetrating the same circle, right? But it is intersecting here and here. This is a secant line, all right? That's at least where the word tangent and secant comes from, all right? A chord is a little bit more tricky though, because a chord, first of all, what is a chord? A chord is a line segment with endpoints on the edge of the circle, which happens to just overlap in this particular case, all right? But it's perpendicular here to the, what would be, if it were in fact on an X and Y coordinate plane. The translation of chord has been somewhat corrupted through the years, and that's what where sine comes from. It's in reference to half of a chord. All right. Now, why is that? The usage of the word sine in reference to the length of half a chord is the result of poor translation from Arabic to Latin. What we're dealing with is medieval math, and the locus of mathematical activity, for lack of a better phrase, in the Middle Ages was in North Africa, all right, and in the Middle East, all right, and in India, all right, as it would be even further back in time. Anyhow, Europeans were using Roman numerals still at this point, and just getting on board with algebra as a subject. Anyhow, there's a poor translation of the word in Arabic for chord, all right? badly translated in that they confused one word with another. All right, I could never do Arabic any justice, but it's like a very slight difference in spelling. All right, and as a result of that, Latin speakers chose a word that does not refer to a line like this. They chose a word that refers to like a bay or an inlet, you know, in terms of oceanography. Anyhow, things are like that. Misnomers sometimes stick. Like, you know, the word awful, it means something terrible, right? But at one point in history, it meant something great. Anyhow, all of the other trig ratios that you see have a co, right? Because the rule essentially complements, implying a relationship to 90 degrees. So, for example, the cofunction of sine is cosine. That's why I put these in the same color. The cofunction of tangent is cotangent, which is abbreviated cot. All right. The cofunction of secant is abbreviated CSC, cosecant. All right. Now, here's that worksheet that I was mentioning. I'm going to fill it in now. Get rid of this. All right. Here is the whole page. Free some space here. And let me add something to this. There is famously the mnemonic device, something to help you remember something. Mnemonic, mnemonic, I think it's spelled. Weird spelling. Mnemonic, there you go. All right, a mnemonic device known as SOHCAHTOA, all right, where the initials are referring to the trig functions and the ratios that they relate to. All right. Anyhow, get that out of the way. I'm going to give them to you in a particular order. If you're following along and you are indeed writing this, which I would strongly encourage you to do, just for the sake of memorizing. Just realize that what you're dealing with here is mostly what is section 7.2. All right. The material of section 7.2 is the subject for today. And the standard position is something that is, although it may be broached, is really for 7.3 and beyond. I want to nonetheless show you these two different versions of the same thing because you can see that they relate that way. All right, so let's start with sine, which is, I'm just going to put capital letters because I believe it will be easy to read. And as far as the input, I'm putting the angle theta. This is a little bit faint. I think this blue needs to cool its heels. All right. And I'm going to try to rewrite that in a darker thing. That's a bit better, yes. Sine of theta. All right. The sine of theta itself represents the opposite dimension in relation to the angle. So if you have a triangle again like this, here's theta, the angle. This is opposite, this is adjacent, and this is hypotenuse, which I'm just abbreviating like with 3 letters. All right, it's the opposite over the hypotenuse. All right. If you were looking at this from the perspective of standard position, which is to have a right triangle superimposed upon a coordinate plane, like this, but this is the x-axis and this is the y-axis. Sine you would just change the labels slightly. So here's sine of theta. This is still not writing very well. Okay. Sine of theta would be, instead of calling it opposite, it's a y dimension. So I'll just call it y, and instead of calling it a hypotenuse per se, it's in relation to a circle, so it'll be a radius. Okay? Anyhow, it is still this relationship, right? These dimensions are in respect to the angle are what a sine function represents, right? So you can put an equals there. All right, I sometimes neglect to do that, and sometimes on purpose. All right. I'm debating whether I should. Alright, there's no sin in putting in equals here, but I just don't want it to make it look like it's anything special right now. Okay. Now the next one would be the cofunction of sine, which is cosine. So COS for cos of theta. And this, in respect of the angle, would be the adjacent as opposed to the opposite. So ADJ for an abbreviation over the same hypotenuse, HYP. Hopefully that is visible. All right, adjacent over hypotenuse. This is the so and the ka of SOHCAHTOA. So, as in sine is opposite over hypotenuse. These are initials as opposed to my three-letter abbreviations. Ka is cosine adjacent over hypotenuse. 2 letters versus my abbreviations. All right. Again, from the perspective of standard position imposed upon coordinate plane, cos would be x over r. It's sometimes more practical to think of things that way. Then there's tangent. Tangent of the angle is equal to opposite over adjacent. This is the TOA portion of the mnemonic. Tangent is opposite over adjacent. Opposite over adjacent. All right. Again, in the context of standard position, it would look like this. Tangent of theta is equal to y over x. Right? If you know those three, you can develop, basically, derive anything that follows. Because what you're going to notice, especially when we get down here to the reciprocal functions, is that the other three functions that were mentioned, namely cotangent, secant, and cosecant, they're just reciprocals of these three ideas. So if you can envision flipping these ratios upside down, that's how you would arrive at the following three of these. So I'll put them here. And again, memorize it in a particular order. All right. So this first, this second, this third. The fourth would be the cofunction of tangent, which is, the reciprocal of tangent. It is a cofunction as well. Cot of the angle would just be this flipped. So if tangent is opposite over adjacent, then you should expect that cotangent is adjacent over opposite. There's no rest of SOHCAHTOA. It's just sort of backwards. All right. In vertex land here, stated position, coordinate axis land, I should say, cotangent would look like this. In respect of the angle, the cotangent ratio would be x over y. Right. Then secant. Right. Secant, SEC, the Security and Exchange Commission, is basically cosine's reciprocal. All right. So it would be hypotenuse over adjacent. And therefore, it would look like this otherwise. These are reciprocals, so this would be r over x instead. Make that a little bit more visible, hopefully. And the last of these six, cosecant, which is the cofunction of secant, is abbreviated CSC theta. Your textbook uses letters T instead of a Greek letter. Not that there's anything wrong with that, it's just kind of weird. Right? Cosecant, you'll notice, will be the reciprocal of sine. So if it's opposite of a hypotenuse, ordinarily just imagine that flipped. Flip your wig. HYP, hypotenuse over opposite. All right, and therefore, it would look like so. Cosecant of the angle is equal to r over y. That looks like a lambda the way I had it. Okay? Again, if you're going to memorize these, and I really would encourage you to, naturally, for sure know these three. All right? And then, if you're going to go further, once you know these three, you can figure out the rest of them. All right? But know them in this particular order: sine, cosine, tangent, and then sort of their reflection, if you will. All right? Cotangent, secant, and cosecant. All right? These, I'm going to put down here some more information in for the cofunctions as well. But before I do, let me point out something. All right? I'm going to illustrate. As I mentioned, these things on the opposite end here of the list, all right, these are reciprocals. All right, analyze the ratios: opposite over hypotenuse versus hypotenuse over opposite. All right. Similarly, all right, cosine and secant, adjacent over hypotenuse versus hypotenuse over adjacent. These are reciprocals. All right. And lastly, tangent and cotangent, opposite over adjacent, adjacent over opposite. These are reciprocals. And of course, the green doesn't work. Okay. Pull your heels, green. All right. Let's see if this one's a little better because it's been sitting in the cup for a couple of days. Doing hard time in the hole. All right. All right. On the opposite sides, as you narrow close to the middle here, you see reciprocals. Now, a practical way of writing them, all right, would be exactly like that. So I'm going to put 3 bullet points here, all right. But I'm not going to put the actual ratio. I'm just going to use the word, all right. So let's start with cosecant. So a little bullet point here. Cosecant of theta is the reciprocal of sine. So without involving the ratio per se, if you're just using the word sine, it would be 1 over sine of theta. And vice versa. You could rearrange it to solve for sine naturally, in which case the cosecant would be a denominator. All right. Next one. Don't go to sleep, please. Sorry. Secant. Secant of theta is the reciprocal of cosine. So it would be the equivalent of 1 over cosine. And vice versa. You could solve for cosine instead, and in that case, secant would be the denominator. All right, one more of these. I'm just going to put it here because I'm running out of space. Is cot, all right, cotangent. Cotangent of theta is the reciprocal of tangent. Therefore, it's the equivalent of 1 over tangent. Okay? Pretty cool, right? I think so. All right. Now, as I mentioned earlier, all right, and you can tell by these letters C here, all right, these are co-functions of something else, all right? And since they are, you can write basically 6 little equations, identities, all right, that acknowledge that relationship, right? Your textbook has a tendency, if you flip through it, to use, again, not theta, but a letter T, and it puts things in pi radians rather than in degrees. I think it's a little bit more intuitive, though, if you write it in 90, because we think of complements probably, supplements, complements from geometry, all right, as being either involving 90 or involving 180. Well, in this case, for complements, you want to involve 90. So let me zoom in on this space, all right, and I'll erase anything that is obstructing, and give you these 6 for reference to remember. That writes doesn't go away. There's a lot of inconsistency I've noticed in the quality of the writing implements that I purchase. Anyhow. Here, as far as the cofunctions are concerned. Alright, let's start with sine. Sine of theta, I like to put things in parentheses. a lot of times people don't do that, has a cofunction that is cosine. So cosine essentially, the value of cosine's function, that ratio relationship, would be equal, whatever the angle is here, all right, cosine would produce the same result if you subtracted it from 90. Essentially is what this is saying. All right. If you looked at it from the perspective of cosine instead, and I'll put this in red just for contrast, then this would be the relationship instead, right? Sine at 90 degrees minus theta. Whatever the angle is here, all right, sine would produce the same answer if you subtract from 90. All right. Here's tangent of theta, which would be cotangent, and it would be 90 subtraction as well. All right. From the perspective of cotangent, its cofunction, you would write it like so. 90 degrees minus theta. All right, last two, secant. Secant of theta, its cofunction is naturally cosecant, and they are off by 90. All right. From the perspective of cosecant, secant is 90 minus the angle. Okay? Sometimes it's handy, especially when we get into, well, I want to say it's either Chapter 8 or Chapter 9. Proving identities, it's nice to be able to sort of toggle between what you're given and maybe a more concise way of writing it. Okay. I'm just checking my work here. No. Okay. All right, let's do some examples finally. So I'm going to turn this off and continue. Maybe get rid of this block and the white here. One thing you'll be asked to do is to evaluate a function given this, a diagram. So one thing I didn't really emphasize, but it was on that last piece of paper, is if you're given a right triangle in any orientation, right, it doesn't have to be superimposed upon a coordinate plane or not. You can use SOHCAHTOA, right? So when you just have sort of a free-floating triangle, use SOHCAHTOA. Okay. All right, to get where you need to go. Let's just say that you have an angle that's not specified up here, and you have dimensions that are written here. 3, 4, and 5. There is a way to find the angle, but for whatever reason it wasn't brought up in your textbook, so I'm going to not mention it right now, which is an inverse function. All right. But if you wanted to, you could evaluate, that is, you get an actual ratio, which is a fraction, basically, based upon these dimensions in reference to this particular angle. All right. Just make sure that you consider what the angle is that's given. Look at the angle. Look at theta. All right. And then determine what is in proximity. Okay, so if this is the angle that we're paying attention to, which is part of the reason why I made it red, all right, let's just see what the labels would be in reference to SOHCAHTOA here. All right, there would firstly be something opposite of this, all right, which is 4, all right, and then there would be something adjacent to this, which in this case is 3. The number 5 is whatever is across from the box that is 90-degree angle. So this is the hypotenuse. All right. Once you've identified those 3 parts, all right, it's really not a problem. All right, figuring out what the sine of theta would be, what the cosine of theta would be, and what the tangent of theta would be. All right. Okay, if the sine of theta is the opposite over hypotenuse, all right, opposite of this angle is 4, the hypotenuse is 5. So you could right away go, all right, well this would be equal to 4/5, all right, fifths, which means 0.8 if you like a decimal instead, right? That's evaluated at that angle, all right, whatever the angle happens to be. The cosine is adjacent in hypotenuse. So in this case, what's adjacent to the angle is 3. The hypotenuse doesn't change, it's still 5. So 3/5 or 0.6 would be the value of whatever this angle is, all right, using cosine, all right? And lastly, tangent would be opposite over adjacent. So opposite of the angle is still 4 and adjacent is still 3. So you'd have 4/3. Okay. Now, having determined those, right, and if you're aware, of course, what the reciprocals ought to be, right, you could go backwards now and calculate what cotangent, secant, and cosecant would be, respectively. So I'm a little short on space, so I'm going to start down here, all right. Using this information, all right, the cotangent of theta would have to be those dimensions flipped. So 3/4, 0.75, all right? And naturally, secant, all right, which is the reciprocal of cosine, would have to be these dimensions flipped. So 5/3. And again, just for the sake of space, I'm going to erase this. The reciprocal of sine is cosecant. So the cosecant of theta, in theory, would be these dimensions flipped, so 5/4. Okay. And those are the 6 trig functions evaluated. All right? They're an actual number. I just want to check something real quick. These are correct. I'm just obsessing over something else. Okay. It doesn't come up at any point in the conversation in section 7.2. If you wanted to, and I'm saying this only because I think it's practical, and it will be revisited at some point further down the pike. If you actually wanted to find the angle that is theta here, if you have these dimensions, for sure you can figure out what they are. So if this dimension is 3, 4, and 5, all right, take any one of the 6 trig functions, all right, more likely you would use either sine, cosine, or tangent, and then use something that is the inverse of that. All right, for right now, what that means is you're going to hit the second button on your calculator, and then the actual trig function, let's just say sine, and what you will glean from this is that you will get something called the inverse sine, all right? And in the function, what you put are the dimensions that you've determined. So 4/5. Right? What you can see from your calculator is, because I already did this, was a whack-a-loon. If you took the inverse sine of the dimensions 4/5, as you see them here, you'd get 53 roughly is the angle degrees. I put this in degree mode, by the way. So if you hit mode, choose, for right now, choose degrees rather than radians. Quit. All right. But if you alternatively went with the inverse of cosine using those respective dimensions, 3/5, you would get the same angle as you should. If you went and used tangent, secant and then tan, and then use the dimensions you determined for that, 4/3. All right, you're going to nonetheless produce the angle 53 degrees. All right. So again, it wasn't actually brought up right now in your textbook, but it just seemed like an appropriate thing because it's practical. It's a way of figuring out what the angle is. All right, we'll revisit that at some point. Okay. Here's a more practical problem: finding a missing side length. That's good advice. In any case, that's why I didn't want to erase it. Let's say that you were trying to find a missing side. All right, and you were given this picture. You have, again, a free-floating right triangle. As long as you know it's a right triangle, they really should put that box in the corner to indicate that non-verbally. And you're given dimensions of 7, and the letter A, which is not very satisfying, and the letter C here. Again, look at the angle, all right, which I neglected to draw, 30 degrees right there, all right, and then determine what is in proximity of the angle. All right. So, across from this, i.e. opposite, is the number 7, all right. What is adjacent to this is the letter A. Right? And again, the hypotenuse is always across from the 90-degree angle. So this is, in fact, the hypotenuse of C. Right? Now, if we're trying to figure out, let's say, the value of A firstly, and then the value of C secondly, all right, we're going to need to incorporate the degrees in this case. The last problem didn't tell you what the angle was, and at least one of the side lengths. So if we have opposite given, right? If we are for sure given opposite, right? Which of the trig functions that we are aware of include this? Opposite, right? Well, here's so, ka, toa, just really quickly, right? Look for the O's, basically, all right? We're given this actual number of 7 opposite of the angle, and we need to decide, all right, in order to get to the answer, what is the value of A, what is the value of C? We want to choose a trig function that actually incorporates that somehow. So look for the O's in SOHCAHTOA, all right? Sine is one thing, all right, and TOA is another. So we're not going to use cosine in this case at all, all right? If we were to go sine of theta, then it would be opposite over adjacent. All right? Not necessarily wrong, but let's compare it with the alternative, which is tan of theta, which would be, pardon me, I wrote it backwards, opposite over hypotenuse versus opposite over adjacent. All right. I'm going to superimpose what is here in the ratios, all right, and see what maybe our best choice would be. All right. We would use 30 in either case for the angle degrees, and it really should be in function style. All right. The hypotenuse here would be C, all right, and the adjacent number would be 7 here. Pardon me, the opposite is 7 and the hypotenuse would be C. All right. In the case of tangent, all right, opposite is still 7 and adjacent would be A, right? So it looks like, because we want to answer both of these values, find the missing side lengths, we're going to use each of these one after the other. It doesn't matter which you use first, but for different purposes. This is going to return A if we rearrange it algebraically, and this is going to return C if, again, we rearrange it algebraically. So, I can erase this now. I'll do that over here. If we went in alphabetical order, we, to solve for A, would have to have A more or less on the normal tier and not as a denominator. So we're going to have to algebraically manipulate this, all right? And in that event, move A and then move tangent of 30. The opposite of dividing by A is to multiply by A. There's a cancellation effect on purpose, and if you've done it here, you're obligated to do it here, all right? That means that you have A tangent of 30 is equal to 7, all right? If you want to solve for A, you would then at this point have to move the tangent function. So the opposite of multiplying by tangent would be to divide by 30, cancellation effect here, and then put it down here instead. Essentially, you're swapping places tangent and A, all right? Which means that A is going to be equal to 7 divided by the tangent of 30 degrees. Right? Just make sure if you're doing this with your calculator, you have it in degree mode. Right? Otherwise, there'll be some problem. All right? Similarly, if you're going to solve for C, you need it on the regular tier, you need it isolated to one side, so I'm going to move C via opposite operations, so times C here, there's a cancellation effect, and plop it on this side simultaneously, and really just for lack of space, I'm going to divide by sine here of 30, cancellation effect, and then put it down here where it would have to be. All right? And then write this a little bit nicer, a little bit neater over here. C, isolated, would be equal to whatever 7 divided by the sine of 30 would be. Okay. So at this point, I'm going to take a calculator, clear it. Again, often make a mistake. Make sure your calculator is in degree mode. You could just move the keys around. All right. And now, enter these features. All right. We'll do A first, just for alphabetical order. 7 divided by the tangent of 30. 7 divided by the tangent of 30. We would sport and close the function here. And you see you get 12 and change. All right, so 12.1, I mean, unless somebody specifies that they want you to round to a certain degree of precision. All right. A would be about equal to 12 degrees. Okay. The other one, same deal, just a different trig function. Enter 7 divided by sine here. Sine of 30, being a twit, putting the parentheses there. That's a good word, even 14. Okay. So C in this case would be exactly equal to 14. All right, whatever the units are involved to begin with. Okay, just make sure they're consistent. Sometimes they like to trick you like that. All right. All inches, all centimeters, all whatever. Let me put my projector back on and then show you the special right triangles. And darken up the room again. And erase some stuff. Okay. Okay, take a gander at this. This actually is funny. I made these drawings like about 11 or 12 years ago. And I did them in PowerPoint. And in that older version of PowerPoint, the triangles were purple. And then when I basically cut and pasted them into a new PowerPoint file, they changed to orange, all right? And although I wasn't really planning on keeping it that way, I kind of like the contrast. So for presentation purposes, at least if it makes it more aesthetically pleasing and easier therefore to understand, hopefully, I'm going to leave it just like it was. All right. Now, these happen to be two special right triangles that you would want to memorize in the long run. All right, the famous 30, 60, 90 degree right triangle and the 45, 45, 90 right triangle. Why are they practical? Because they have, regardless of what the actual dimensions are here, they always have these proportions. All right, so if this is oriented in standard position, say hypothetically this was on coordinate axis like that, all right, and this was an x value, it would be the length of this leg of the right triangle would be the square root of 3, so something like 1.7, all right, and proportionately the y dimension here would just be equal to 1, and the hypotenuse would end up being just 2, all right. It would be referred to as r because it would be something like the radius of the circle, all right. Here's the Pythagorean theorem, just with those little tweaks. All right, instead of a, b, and c, it's x, y, and r, for the sake of having it on a coordinate plane and involving a circle. All right. Here's the alternative, the 45, 45, 90 triangle. These proportions would be 1 and 1, and the hypotenuse would be the square root of 2. Right? There is another way that may be more practical sometimes, so I'm going to write it right now in an obvious red color. Right? Instead of just calling this, say, 1, all right, if what I am saying is true, all right, that the proportions, regardless of the actual measurements of these things, would always be the same consistently, you could call this alternatively S, because it would just be 1 times S, you know, so that's not changing anything. Whatever the value is, S, it's not really writing that great. Put this here. Call this 1 times S, or just S, right, really. And therefore this square root of 3, alternatively, would be the square root of 3 times S, right? And the hypotenuse would be twice as much S. Right? It is sometimes practical to think about it that way. Right? It isn't changing anything, it's just making it more obvious that you can then figure out what the y dimension is, all right, an actual measurement, it's like 15 inches, say, whatever, you know, or 15 centimeters, whatever you have, all right, and then figure out what the dimensions would be here and here by just multiplying by the square root of 3 or multiplying by 2, all right. Similarly, these would both be S, right, side, side, all right, and this would be the square root of 2 times S. Just realize that the value of the S is outside the radical. It's not really in part of it, right? The radical is more or less acting like a coefficient. Okay, so know these dimensions, right? Along the length between 30 and 90 is the square root of 3, all right? Between 90 and 60 is 1, and the hypotenuse would be 2. Or if it's 1 and 1, then this is the square root of 2. All right. All right, let's do some examples again. And if I have to, I'll draw that again. Are we on light here? Pretty good. Okay. Let us try to find trig functions find the exact value, which means no rounding, of the 6 trig functions of pi over 3. In other words, evaluate those functions using pi over 3. Now here's the thing. If you're given something in pi radians, as in this case, all right, if it helps, all right, convert pi radians to degrees first. All right? This is sort of a preliminary step. I don't want to corrupt you, but that's just the way that I was always taught to think. If you are given pi over 3, and you employ the correct conversion factor, just to bring back the subject of last time, then this will give you what you want. Right? In this case, what is given is pi radians. All right, so I'm going to use the appropriate conversion factor to give me degrees. All right? The conversion factor in this case would be something that cross-cancels pi, so I would have to make it a denominator. And then the equivalent of what pi is, in terms of degrees, is 180. Right? That means that after the cross-cancellation effect, namely here and here, what I'd have is 180 divided by 3, all right, which is 60 degrees. All right? Having done that, right, you go, oh, all right, special right triangle. Ooh la la, all right? And then you remember this diagram. Right, and you go, all right, well, 30 here, and a 60 here, and a 90 here, all right, would have these dimensions. It would be between 30 and 90 is the square root of 3, between 60 and 90 would be 1, and this would be 2. All right. So now we're going to find the exact value, which means they're going to be a ratio, there'll be a glorified fraction for each of the 6 trig functions. Do the first 3, and then you could make the mirror image of them. There is going to be a little bit of a hiccup in between because there's a radical involved here, but it's not something you can't handle, and I'll fix it when we get there. All right. We'll start with this. Sine of, instead of putting pi over 3, which would be what's given here, make it the more obvious 60, all right, would happen to be what is opposite of 60. So square root of 3 over the hypotenuse, SOHCAHTOA again. So square root of 3 over 2, right? This is why in the instructions they specify, I'm stealing this from the book, exact answer or exact value, because they don't want you to round anything that is an irrational number. All right? Why? Because if you don't round it, if you just leave it as the more or less the abbreviation, it summarizes all of infinity without chopping off. All right? So that's the exact value of sine using that dimension of an angle measurement. All right? Let's do cosine. Cosine of 60 would therefore be what is adjacent to 60 in this orientation is the number 1. So it's 1 over, what's the hypotenuse still? 2. So it's a half in this case. And then tangent of 60 is, and I really should put degrees, is opposite of 60, square root of 3 again, over adjacent. So that means, I'll put it in green just to contrast maybe. It's not going to show up. Square root of 3 over opposite over adjacent, which would be 1. Now you could leave it as square root of 3 over 1, or you could just simply reduce it to, well, it's the square root of 3. The advantage of leaving it like this is that when you're looking for the reciprocal, you'll know what the top and the bottom ought to be because you wouldn't have erased it. Right? So I'm going to leave it like that for right now. All right, square root of 3 is a better answer. It's just 1.7, whatever it is. All right. Now, if we've gotten those three, all right, then you can calculate, all right, their reciprocals. All right. So, I'm sorry, my eyes are itching. The reciprocal, and coincidentally also its cofunction, all right, of tangent is cotangent. So the cotangent of 60 would be these dimensions flipped upside down. Now here's where the hiccup is going to occur, and I may have to move my little card here. All right, 1 over the square root of 3 is in fact correct. All right, the thing is, it's bad etiquette. All right, so let me just scoot my little card out of the way. All right, and make a speech. I need a little space, so I'm going to put this out of the way. You may or may not remember this subject of rationalizing the denominator. All right. Basically, in the years before they were handheld calculators, all right, in which case you wouldn't be able to get, you know, something of a gratifying decimal answer instantaneously. A person would be taught to not leave something like this even though it is correct. What you would do is you would write an equivalent via the process of rationalizing the denominator. All right. What that essentially entails doing is taking something with maybe a radical here and rewriting it so that the denominator doesn't have a radical. Right? So you would end up multiplying by a convenient ratio of the equivalent of 1. Right? By ratio, I mean something with an obvious top and an obvious bottom, but overall still being equal to 1. Reason being that if you multiply anything by 1, you're not really changing anything but its appearance. So we don't want to change the value of it. 1 over the square root of 3 is indeed correct. It's just inconvenient, more or less, to have a radical in the denominator. All right, without a calculator at least, right? So what we'll do in this, what usually is the case is, and for our purposes immediately, whatever radical you see here, as long as it's a square root, right, you're going to replicate it right next to it, all right, because that's going to form a convenient ratio of 1, which although is not going to look like the number 1, if you had the square root of 3 here, and then you multiply by the square root of 3 over the square root of 3, square root of 3, granted, is an irrational number, 1.7, whatever it is, into infinity. Something ugly divided by itself is still what? It's still 1, and multiplying by 1 is not changing the value of something, it's just going to change its appearance. So the effect is that you would have 1 times the square root of 3 above the line now, all right? And then the bottom would be the square root of 3 times itself, all right? Essentially the square root of 3 squared. So these are opposite operations. What happens when you have opposite operations? There's a cancellation effect, right? So this is the effect, all right? You end up with the square root of 3 over 3, right? If you've ever had in maybe Algebra 2, something, what do they call that? I'm trying to think of, when you have a complex number or something like that. There's a similar technique for that when you have a complex denominator, all right? Anyhow, this is known as rationalizing the denominator. It's basically changing the appearance of something. All right, preserving the value. Because you're writing an equivalent expression, right? So what you end up with ultimately is this: the cotangent of 60, all right, would be the equivalent of whatever 1.7 divided by 3 is, all right? So the square root of 3, all right? Here, I'll do it. What I'm going to, just to prove a point, because I'm obsessive, All right, let's take tangent of 60 and see what we get as a decimal, right? The tangent of 60 is 1.7, whatever it is, whatever the square root of 3 is. So, tangent of 60, all right? Sorry, 1.7 and change because it's a square root of 3, all right? There's no button for cotangent, but you do know, all right, that the reciprocal of cotangent, well, pardon me, cotangent is the reciprocal of tangent. So if you wanted to, you could write this instead, all right? And that value entered in your calculator should produce this, all right? Which would also be equivalent to that in theory, all right? So 1 divided by the tangent of 60, because I have it in degree form here, would give you 0.577, whatever it is in change, all right? That's what the value of cotangent actually is, all right? Since I have rationalized this as square root of 3 over 3, that's what I should get, all right, as a decimal. So I'm going to write that now. If it doesn't, I'll have egg on my face, all right? And then I'll just think about it, but we'll see, all right? Here's the square root of 3 over 3, same decimal, right? Rationalized. Even if I didn't rationalize it, even if I left it like that, and it would be considered bad etiquette, so don't do that. 1 divided by the square root of 3 should be the same decimal nonetheless. Yes, indeed, 0.577, okay? So go the whole 9 yards, all right? And if you want to verify that something is correct, remember that the cotangent, the secant, and the cosecant are the reciprocals of something. In this case, it's reciprocal of tangent. All right, now, just to finish up, we'll do the other two. All right, so the reciprocal of cosine is secant. So the secant of 60, therefore, would be this ratio flipped, therefore it's just 2. Right? If it's 2 over 1, it's just 2. Right? Card back. Yeah, that's inertia, which I neglected. And I hopefully didn't break my mug. Enough friction on that. All right. As it went flying. All right. If there was any other markers, get me. I'm going down to go find them. All right. Nope. Okay. Sorry. I'm going to. All right. Inertia. Behave yourself. Dad named the name of a child. I'm going to name your child Inertia. All right. All right. So. Yeah, this was the problem to begin with. All right, there you go. It's obscuring the results. All right, so one more. Sorry, this is taking so long. The cosecant of 60 is the reciprocal of 2, the reciprocal of sine. So if it's the square root of 3 over 2, which is fine, right? It would, in theory, be 2 over the square root of 3. I'm going to erase this horrified math face, just for the sake of space. All right. All right. And then we have the same issue again. All right. Bad etiquette, where you have a radical in the denominator. All right. So we're going to multiply by a convenient ratio of 1, just to change the appearance while preserving the value of something. So the effect is going to be nonetheless. Since this is a square root of 3, all right, it would be the square root of 3 over the square root of 3, all right? That's equal to 1, so the top would be 2 square root of 3, and the bottom would be just 3, because that's the effect of radical times itself. And this is your answer. Okay, 2 square root of 3 over 3, all right? Remember that, all right? Whenever you have to rationalize something, and it is really just to get the radical out of the denominator, it's pretty, not 100% of the time, because it really depends on what type of radical it is. If you had a cube root, you might be a little bit more strategic than just replicating what is here and here. But for our purposes in the immediate future, basically you're going to take whatever you see here and then write it as something over itself, right? And then straighten it out the arithmetic. Okay. Is that okay? I'm standing in the way. Okay, fine. Moving on. There's two more questions, and then I'll stop for today. That's what I can, and I'm going to probably have to hit this with, I think, alcohol. I get rid of the blow, because it's just so tenacious. It's not really working. Now, your textbook being the oddball that it is, if you get questions like this, and it's the only reason I'm mentioning it, all right, I might ask you to more or less test out a cofunction identity, all right? So, if the cosecant of pi over 6 is equal to 2, use that information to find the secant of pi over 3. All right, now, if you recognize, all right, from the activity earlier that there is a relationship between these things, I mean, their names alone kind of suggest that. This is cosecant, all right, and this is secant, all right. There's a relationship from cofunction identities, namely that the secant is the cosecant offset by 90, all right, and vice versa. Cosecant of theta is the secant, 90 minus the angle. If it helps, and I think it probably would, at least until the point that a person recognizes what these are in degrees, convert them. So let's do that first. All right. It's a review of the exercises from section 7.1. All right. First of all, pi over 6. This is pi radians. All right. Let's go to degrees. All right. The appropriate conversion factor would be the one that cross cancels pi and leaves us with degrees. So pi over 180, oriented like that. All right. The effect, pi symbol cancels, and then this is just 30. So this is equal to 30 degrees. All right. The other one, and I'll put it here, 30. All right. The other one, and you might have already guessed, pi over 3, incorporating its convenient conversion factor that goes from pi radians to degrees would end up being 60. All right. So in here, I'm going to put 60 in place of pi over 3. All right. Now, here are the cofunction identities. All right. We're looking to find secant of 60. Sorry. And we're given this. All right. So let's start with the cofunction identity. For cosecants, all right, which is this. The cosecant of whatever angle, theta, should be equal to secant, say cofunctions, of 90 degrees minus that angle. And I'm going to fill in the information that I've just had in degree form, which maybe is unnecessary, but I like to. So, if the angle is, in fact, because it was pi over 6, 30 degrees, all right, and we already know that this is equal to 2, all right, I'm going to put 2 is equal to, that's what secant is, because we're trying to evaluate secant. Now, maybe it will blow up in my face, but we'll see. All right, over here, if I took the same angle of 30, and put it here, 30. What is the difference of 90 and 30? Probably not a coincidence because they asked us, right? Well, it is in fact the thing that they're asking us about, which is 60. So therefore, secant of 60 degrees, otherwise known as pi over 3, is just 2 as well, right? Because they're cofunctions. It's kind of just verifying something that is true, all right? Not especially satisfying. Right. So, if you want to write it all nice, all right, I'm not going to put it in blue, it's always a mistake. The secant of, I'll put it in pi over 3, is just equal to 2 as well. That's what it verifies. All right. Okay. All right, last question is an indirect measurement question. So I'm going to draw a picture. Example of indirect measurement. All right. We're going to find the height of a tree. All right. It is arguably a good idea to involve trigonometry to calculate indirect measurements, because some things would be very difficult for an average height person to do, like measure the height of a tree. So here's a tree. Let's pretend it's a redwood. Right? And yeah, in keeping with the theme, make it a pine tree. All right. I think I may just. That's not let me turn the light on. Is that on? It's debatable. Right. I hope that makes it a little bit easier to see. Otherwise, I'll turn on this light. Yeah, that's better. All right. Yeah, I want both of them. All right. If you have some dimensions given to you, I have to replicate that because I didn't print it. Suppose that you have some semblance of a right triangle here, strategically so, that along the base, because it would be easy to measure things terrestrially, right, rather than vertically, because you're not fighting gravity, of 30 feet, all right? And you have a sextant or whatever measuring device you have, a person standing here, is looking up, all right? All right, and they measure that the angle from the tippy top of this, from where they're looking down to the ground, would be 57 degrees, all right? Using these dimensions, all right, the measurement of what is known as the angle of elevation, all right, and the measurement of from here to here, base, basically, base measurement, right? We could incorporate a trig function and figure out how tall this is, right? But we'll have to decide for ourselves, right, which would be appropriate, right? If again, you kind of think about this as being on a coordinate plane, and this is an x dimension, then this would be something of a y dimension. All right, if it's just a free-floating triangle, alternatively, theta, 30, and then we don't know what that dimension is. All right, in respect of this angle, all right, either without it known or known. All right, let's consider, all right, let's look at the angle theta and then determine what is in proximity. What's next to it, basically. All right. The angle here, 57 degrees on theta there, all right, is adjacent to 30 feet, all right? So if you remember SOHCAHTOA, if you have a reference of some sort, or you like the standard position version of the trig functions involving x's and y's and r's, all right, we're going to choose the thing that incorporates that, right? Choose the trig function that incorporates, all right, adjacent somehow. We have a couple of things, right, to choose from. Cosine maybe is the most obvious. Cosine is adjacent over hypotenuse. And then alternatively, we have tangent, which is adjacent over, opposite over adjacent. Right. The dimension that is across from here is not a hypotenuse, all right? It's opposite of it, right? So if I had to choose between cosine and sine, I would want the one that involves the thing that I have and the thing that I'm looking for. So we're going to go with tangent ultimately. Okay. Need a little bit of space, so I'm going to erase this. All right. So tangent of 57 degrees, because that's the angle that we do know, all right, should be equal to what is opposite of it, the height of the tree. You can call it y, you can call it h, all right, h in this case, over the dimension of 30 feet. All right, I'm going to put the units. All right, in this case, all that we have to do is just manipulate this algebraically to isolate the height that we're looking for. So the opposite of dividing by 30 feet is to multiply by 30 feet. There's a cancellation effect, and then you plop it over here, 30 feet. So height of the tree should be 30 feet times the tangent of 57 degrees. All right, I'll take my calculator and do that. All right. 30 times, let's see, tangent, that's inverse, sorry. I'm reading it backwards, it's always a problem. All right. 30 times the tangent of 57. All right. 42 and change, right? Or was that 46? No, that's 46, good. All right. So the height should be 46.2 if you rounded it to the 10th place feet. By feet, because that was what the unit was of the other dimension. Okay? Now, just so I won't be remiss, if your textbook, any of the homework problems, starts asking you about something called angle of elevation, or referring to angle of elevation in tandem with something called angle of depression, let me just take the opportunity to explain what that is. It's not really anything special, but it is a little weird, all right? If there were an imaginary line, just to clean up this picture a little bit. If you're looking up to the top of something, the angle here terrestrially, this theta, up to the tippy top of something, there's your eyeball here. A nice little mascara eyes. That's known as the angle of elevation in the context of certain problems. So don't let that trouble you. It's just giving a name to something that never had a name otherwise. Looking up is an angle of elevation. All right. If, on the other hand, a person was standing here, maybe an alien, floating, all right, their little alien body, and looking down, all right, the angle that would be equivalent, angle here, right, not the one in here per se. All right, looking down from straight out this way, reading this way, as opposed to reading that way. This is known as the angle of depression. It's so depressing. All right. What's the point of any of this? Well, they gave names to these dimensions here, but if you're familiar with geometry, you might recognize their equivalents, all right? So I'm going to take the time to explain that. The angle of depression should, in theory, be equal to the angle of elevation because, right, they're alternate interior angles. Right, you may, in your vaguest recollection, remember alternate interior angles, corresponding angles, and alternate exterior angles. Right? Alternate interior angles are essentially equal to one another, whether you give them a name or not. All right? They come from the scenario of having parallel lines that are crossed by a transversal. Right? These are parallel. This would be a transversal. All right? And specifically, this, whatever it is, and this would be regarded as equivalent alternate interior angles. In this scenario, it would be called an angle of elevation, and if they felt like it, the angle of depression. There's another pair of them as well. All right, whatever this obtuse angle would also be considered one of the alternate interior angle to whatever is sitting here. Right. So, alternate interior angles are equal. Therefore, angle of elevation and angle of depression would be equal, at least if it's drawn this way. Okay, that's it for today. All right. I'm going to give you homework that pertains to section 7.2. All right, this video is for Wednesday, so I'll see you again on Thursday tomorrow. Okay, be careful out there.